And central engine produce ejector, and ejector produce gamma burst. And when this ejector interact with the interstellar medium, we have later observations like afterglows, multiple energy emissions. So this is the physical direction when we try to understand the model. But observationally, we actually start from, in most cases, we start from a single GRB. For example, this is in most cases, when we observe a GRB, we see a gamma burst only in gamma rays. Then we can infer its emission ejecta. And from the emission ejecta, we infer the central engine. From central engine, we can further tell progenitor can this system be. So this is observer path. In the cases like this one, that's it. And but in some cases, we have rich data, including the afterglow, kilonova, supernovae, host galaxy gravitational wave, or even neutrinos. Then we get more information, and we can further, for example, directly decide a progenitor from gravitational wave. From kilonova, we also have something from the model product. So, but this is the very way. We need multi-wavelength observations. We need very quick follow-ups. This is what the automatic telescopes do, and also I believe this is the theme of this conference. So from like 50 years of data, we build up a standard understanding of gamma burst, and this is what we expected. We know this gamma burst can form from collapse or merger. We know there should be central, which consists of black compact star or like black hole with a disk with ejector. We know there should be prominent in phase, afterglow phase, and sometimes we should have supernova for GRBs and kilonova for short GRBs. We also have some host observations, and this all build up a standard framework of gamma burst. And but in this talk, we can go further, and even this is standard, we still have a lot of new things. And this include within the standard frame, we still have a lot of things not fully unstable. For example, the precursors, the prompt multi-wavelength observations. Like we do not have so many optical prompt emission observations. We do not have so many radio observations in the prompt emission. For the afterglow, we are also lack of observations. And we only have a few cases of orphan afterglows. And this was talked by Vladimir. And we also do not have a large sample for kids. And even we do have some new types of GRBs, like ultra long GRBs, ultra short, ultra and GRB related to other unusual and subthreshold GRBs, and Gen 4 GRBs, and orange GRBs. So in this talk, I'm going to focus on those new types of GRBs, new types of observations. And in order to study new topics, I'd like to summarize that all those new types of observation tells us new radiation mechanisms and new physical origins. So I'll divide it to three different topics, and the first one is transition on the central engine. And different, that means central object can be non-standard from the standard framework, and even the property GRB can be a totally new object. Okay, let's go for transition. So our study transition is, so why we should have a transition for different GRBs. And I think the first reason is the ejector radiation condition control. And this is the reason one. And reason two is that the further collapse of the central object can cause a transition. And observationally, what do you expect is that, and you can expect the spectral change, energy change, and also naturally you can expect the multiple episodes of the prominent emission. So I'll show you this textbook of transition in this burst. So GRB 160625. And this burst contains three different phases. The first one is a short GRB with only 1 second duration. And second one is a long GRB with 20 seconds or 30 second duration with very bright flux. And then after 200 seconds, long tail, but it's, in principle, you could still define as a long GRB. So 3 sub-bursts with 1 single GRB. So short plus long plus tail. And actually, also different. The first one is thermal, and second one is non-thermal, and third one is soft non-thermal. And how do we explain this? And then we can infer this to the physical conditions, which are determined by the dominant variable transform to a Poynting flux dominated flow. And what's the physical reason for that? Actually, further infer that, and this is caused by very special central engine, which can be strongly magnetized engine with central object being the whole magnet. Okay, this is transition. And the second topic will be different. The central engine, central object can be non-standard. So let's bring this burst again. So the question I want to ask is that, what about if we only observe first burst? So let's look at the first burst. So this is the first burst, it's only 1 second. However, if we put this short burst into the Armative relation, you can see A, the burst A, is well face the long burst track. But there's no problem for this because we know this is the precursor of a long GRB. Right? But the point is that what if we didn't observe the long duration second and third burst? And we have one burst. This is 200826A. By definition, it's a short duration GRB, lasting only for 1 second. How special this burst is? So first of all, it is very bright. The signal frequency rate is very high, right? It's way above the background. Okay. And the host galaxy, you can measure the host galaxy with a redshift of 0.7, and you can further measure the star formation rate. And it turns out those properties are very consistent with the typical star forming host galaxy for short GRBs, which is type 2 GRBs. Okay, the host galaxy. And you can further fit the spectrum and energy. It turns out the epoch is not very high, which is typical for long GRBs. And you can also further erode the total energies. Once you have those two, you can pull this burst into a Armative relation. Its phase very in the long burst track, which is consistent with the classic model. Right? So remember, this is a short duration GRB. We didn't observe any further emissions. So it's only a short duration GRB, but it's a long burst track. Okay. And the smoking gun is that this burst is associated with a supernova. You can see the optical observations showing that there's a bump. in about 1 month time scale. So a supernova always means a massive star, right? Then we have a problem. First, short. It's definitely short. What's my feeling about it? Because the signal-to-noise ratio is so high, you cannot define this burst as the tip of iceberg effect. So this is the shortest long gamma burst in the history, and everything else is considered long the short duration. But what is the problem for the short duration? I would say this is a very challenge, because we do have a line that short GRB can be plenty long. You can make a short using the extended emissions and make a long GRB. This is okay because you do have different instrument with different sensitivity. Make a long GRB, okay. You can also make a long GRB to a short one. You can argue that maybe the burst is very far. You only observe the tip, right? But this burst is different, and it's not a tip of iceberg effect, because if you believe this effect, you should observe a very fat burst with a low signal-to-noise ratio, right? Okay, you cannot. This is not this one. Another challenge is that if you believe this burst is consistent with the long GRB, but long GRB cannot be intrinsically short. And this is because if you believe long GRB originated from massive star collapse, and this time scale is related to the density of the massive star envelope, right? And this density, you cannot have so much freedom. If you put a typical density and a typical time scale of a long GRB will be hundreds of seconds. You can introduce a coefficient like 0.1, and you can make it 10 seconds, but you can never make a 1 second duration from a massive star collapse. So that's a problem. And unless you make the density very higher, but then again, it's not consistent with the massive star material, right? It will go to the white dwarf material. So a successful theory should explain this. It should reproduce a short duration. It should not involve with the tip of iceberg effect. It should explain all the properties consistent with long GRBs, and also should explain why it's so rare. So how to make it? We don't know yet, but we do have several options. One is that you believe this is short, and in order to make it short, as I said before, you can make the density higher. Then it had to go to the white dwarf density. And white dwarf cannot collapse, right? Then you have to introduce a white dwarf merger, like white dwarf with a neutron star merger. So that may help. I'll talk about this point later. Or you can change the search engine. For example, and this is not powered by the accretion, then you can use neutron star powered short duration GRBs, or differential rotation powered GRBs. So that can make the relatively shorter duration, and this has been discussed in the literature. On the other hand, you can still argue this burst is long. However, maybe the ejecta is not so strong. You need some time to break out the stellar envelope. So the breakout time can be 9 seconds. Central engine time can be 10 seconds. So 10 minus 1, 9 is 1 second. So that may explain. But problem here is that you naturally introduce a weak ejecta. It should not give you a so strong burst. Okay, similarly, you can argue that the central engine is dirty. Your baryon loading is high, and the relativity effect is not so high, so you can actually explain the short duration. But again, this is not, presumably this is not a strong GRB. So there's not very consistent with observations. Okay, what about the White-Dwarf neutron star merger, we do further investigate this model, and turns out if you have a neutron star White-Dwarf, they may form a TZLO object, and the collapse of a TZLO object can further form a GRB with such kind of short duration. So this is not if the merger itself produces a GRB, it's a collapse of the merger product of a TZLO product from the GRB. And we also studied further this heated ejecta material can form something similar to a merger nova, and this when the shell interact with the heated ejecta material can form a late-time bump. Actually, this bump is consistent with a possible supernova bump. And also this kilonova features can explain the optical observations. So maybe this is one of the solutions for this particular GRB. Okay, this is the transition. And alternatively, what about another scenario that we really missed this kind of main emissions, like a second burst and extended tail? And we believe, if you believe this burst is similar to this 160625b, but you only see this one, then the problem becomes how do you miss those guys, right? First of all, let's compare this 200826A with this 160625b. If you compare these two bursts, actually you can see that this precursor is very similar to this one. And then the only problem is that how do you miss this one? And if we compare these two bursts, multi-relation and the spectral evolutions, actually these bursts are very similar. Okay, how do you miss this one if we believe there is one? In the paper, we propose that maybe you have two options. One option is that the jet is processing, and the observer is here. And during the main emission phase, maybe the jet is processing to another direction, and the observer happen to miss it. And another option is that maybe this GRB is in a binary system, and there is a binary star. There is for example, binary stellar, or something big enough to block the field of view of the observer, and you didn't see the main emission during this time. And you see the precursor and here, and later on with the object rotate to this direction, your observer didn't observe this part. So that's maybe explain this burst using only the geometry effect. Then you don't need to introduce additional central engines or progenitors. Okay, maybe this is a very particular short duration GRB from a massive star collapser. If you believe we need additional physical pictures. But what about the opposite case? This is a particular short duration from a collapser. And very recently, we have another opposite case, which is a long GRB from a merger. So a short duration from collapser and long duration from merger. So this is a GRB 211211A. You can see this burst at a very short, long duration with 10 seconds main emission and 70 total duration considering the intended emissions. And surprisingly, there's no supernova, but you observed a very strong kilonova complement. So this is a very challenging again. The problem is how do you, because we have kilonova, you have to agree this is probably from a merger event. But how do a merger event produce such a long duration? Again, this time scale can become a problem if we believe there's a neutron star merger, so you can go to 3 seconds, 5 seconds, but 10 seconds, 13 seconds, or 70 seconds in the total duration, it's very challenging. So we're still studying this burst, and you can see the object is so, this field is very challenging and very new in the observations. Okay, topic 3, its progenitors can be new. Then I'll give you this example for GRB 2004 15A. And this is the first spectrally confirmed short GRB from a magnetar Zhang flare. This is no longer a collapse or merger, but from magnetar Zhang flare. Okay, so the special property of GRB is this GRB is that the host galaxy is very near. It's only 3.5 MPC, very bright, very high energy, with high energy GeV detections. And this is not the first argument from Zhang flare GRBs. But the previous case, we do not have smoking guns because they are too close. But for this GRB, we measure this spectral in very detail, and we actually measure the different energies of the photons. You can see the different energy light curves. They tracking each other very nicely with almost the same time scale, same arriving time scale, and also have the LED emissions. And see the lags is perfectly zero, which means the emission region should be very small. And this again supports the variable model from the magnetar. We can fit the spectrum using different time intervals. Surprisingly, using only like 10 seconds, we can fit the spectrum very nicely with blackbody complement. And this again consistent with the variable model. How do you explain this? People argue that this should be a thermal emission from the magnetar surface, but how far is its emission region? And actually, no previous literature has that detail. And in this paper, we try to further investigate this picture and argue that there should be expanding variable from the magnetar surface. So the emission should come from here, which slightly outer region of the magnetar surface. I'll not go too much detail in this picture, but this picture fits the observational data very well. I would call this a componentized variable bubble model from the magnetar surface. And if you compare this burst, this Zhang flare GRBs with short GRB and long GRBs, and those guys are very nicely form a third track. And if you consider this kind of Zhang flare GRB populations with soft gamma repeaters, you can see the soft gamma repeater burst actually can be extended from this track. So this is a very a good spot of this GRB from the magnetar regions. Okay, so if this is a magnetar, so it seems that GRB progenitors are all kind of related to magnetar. So this is a stable magnetar. There is a Zhang flare magnetar. And short GRB and long GRB are both the those both can produce magnetars, right? But how old are those magnetars? For GRBs and supernovas, we can produce newborn magnetars, but this is an assumption. We never directly observe these newborn magnetars. We have indirect evidence for that, but we never observe this directly. And pulsars, and we do have some measurement from the frequency and period, right? We know that this can be 10,000 years magnetars. Zhang flares, and they're supposedly to be young magnetars, but how old are they? And we actually did, before this work, we do not have a direct support or direct evidence to measure their age. So the essential parameters will be the period and the period derivative of the period. Right? We do have one measurement for the same exact GRB, and in this paper, Alberto try to measure the frequencies of the GRB, and it turns out there are 2K and 4K hertz of QPOs, but this is not a rotation period. It's not, you cannot argue this is from a rotation because it's too high. It may be related to the oscillations of this magnetar surface. So this is one good try, but we still don't know the age of this magnetar. But we may have found one from this GRB. This is 130310A. This is a very old GRB. And during this phase, you can see this GRB is very like a giant flare with a very sharp peak with extended emission. And during this extended emission, we see several very nice period signals. And when you try to measure the period using the pulse spectrum or other wavelength method, actually decide a very strong signal of the period. It's 10 to 12 hertz. And we convert this to the period, it turns out to be 80 milliseconds. And you believe this period is a rotation period. And because it's a giant flare, it might be the giant flare, and giant flare should be magnetar. Then you can assume a magnetar magnetic field, and you put this magnetic field into this equation, you got the P dot, right?
3 minutes, excuse me. 3 minutes.
Okay, I'll finish very soon. And then you have P and P dot, you can measure the age. And P over P dot, it turns out to be only a few weeks. So you put this age into the P and P dot period diagram, it turns out this person in this region. So this is a newborn magnetar from GRB and supernova, and this is old magnetars from here, but this is the first one we discover a magnetar in this region. So this is a very surprising GRB, which might be another magnetar giant flare origin, and which we also have the age measurement. Okay, so this is the third topic, and progenitor can be very new and can be from magnetars. So I'd like to conclude that it should be a time to be open-minded from GRB origins. We do have different origins like magnetars, or in the future we can detect some neutron star black hole mergers. We can also detect the neutron star black white dwarf mergers in several cases. So I think that's all my talk, and we are going to get new observations with growing missions, growing observational instrument, and we should expect more in the future. And I think that's my talk. Thank you very much.
Okay. Please, questions? Vladimir Mikhalovich?
У меня больше discussion.
Maybe discussion after questions. Maybe questions? Yes. Alexander Vasilievich Tutukov.
There are two evident models for gamma bursters: disruption of neutron star or disruption of white dwarfs. Couldn't it be some types of gamma bursters, what you introduce, be only just a result of point of view from pole? We have a cylindrical, symmetrical situation in the case of merging, and you could see on this situation from the equator or from pole, and to my understanding, the picture could be very, very different. So point of view and for new types of gamma bursters.
Okay, do you hear the question?
Yeah, I hear there's some echoes, but I think I hear most of the question. I think it's more like a comments. I agree that white-dwarf neutron star merger is a totally new kind of scenario. People have proposed this model to explain long GRBs, but in order to explain these short GRBs with additional theoretical investigations, but still this is ongoing. We still have a lot of things to understand, but this is just one of the solutions in our paper. Alternatively, people argue that this may be a black hole neutron star merger or something else. So I'll be open to other theories as well. Thank you for your question.
In short form, this question is the following. Sphere is always sphere, but disk, it depends on point of view.
Disk. Sorry, I didn't hear the last sentence.
Also, I would ask you, maybe I miss it, but typically long and short GRBs also differ from spectral hardness. And as it is well known, long GRBs are more soft and short more hard, have more hard spectrum. Have you taken it into account, or your analysis based only on duration?
Oh, of course, we have to consider the spectral properties. Yes, the hardness ratio. Or on the other hand, we can measure the spectral properties, right? And so that GRB, or that particular GRB, 200816A, the 201211A, they are both consistent with the different origins because of the multiple properties, including spectral properties. Yeah.
Okay, thank you. Any questions? No? Please, Vladimir Mikhailович, we'll discuss.
Не надо, Владимир Михайлович. Lipunov, Vladimir Lipunov, I would like to not discuss it. Some added, maybe you give a comment to my opinion. Is it possible show my slide? I would like to show another conception of the GRB is a spinar paradigm. I would like to show, no, Danilo?
You can show your slides. Maybe you can stop. I don't know how to stop. How can I?
Very long time ago, we proposed the spinar paradigm. That is a collapse of the very high angular momentum collapse. And I would like to show you our diagram from the paper Astrophysics Journal Letter 2007. That is our paradigm. That is explaining the different type of GRB. You see on this axis the high magnetic energy of the collapsed nuclear of the star, as that is a specific angular moment. If the like to the Kerr parameter, analog of the Kerr parameter, you see if the Kerr parameter is less than unity, you see only supernova. If the angular moment is big, you see very long events, very long events. If you see very magnetic, you see very short events. And in this model, very understandable the precursor and main GRB peak. And you see 1, 2, 3, 9 type of different gamma ray bars behavior, including the plateau. And this scenario included Magnetar is very specific case of this picture, when the mass of the neutron star formation is less than when the mass of the spinar less than the Oppenheimer-Volkov limits. In this case, naturally included the magnetar, but magnetar only one possibility. The more interesting possibility is the spinar. That is, in English, you can see this paper, and we publish it after that, 2 papers in monthly notices, but not popular in the West, and this may be you interesting. Can you sum it?
Thank you for introducing this paper. I'll take a look, and seemingly this is a very uniform and completed model. I'll take a look into that. Thank you.
Thank you. Let's thank again. And the next talk is by Sergey Simakov. Are you here?
Наверное, нет. С утра не было, онлайн нету его. Он отдыхал в Крыму, но должен был вернуться.
Ну что, пропускаем?
Да, следующего давай.
Yes, we should miss it because Sergey Simakov is absent. Then, please, YiQing GUO, if I right.
Это мой телефон.
YiQing GUO. Включен он? Как правильно это назвать?
Ну, он, наверное, не знает, что ему надо выступать. А тут кто-нибудь...
Не, а как не знаю, он же стоит.
Да, но он по другое время стоит. 13:10, понимаешь? Хотя вон сколько сейчас.
Дороже сейчас так и есть.
Так и есть. Все, давайте ждем. Сейчас, минутку, подождите. Он в списке есть.
А можно ему в чате написать, что... Поехал. А это кто? Просто мастер? Кто это имеется в виду?
Тебе дали, наверное, первоначально.
Да.
Окей, я спросил Наташи, сейчас она замотана. Ты опусти это самое. Ты, главное, не гони, потому что время теперь есть.
Ну, я хочу гнать.
Да. Может быть, какой-нибудь доклад отсюда можно перетащить.
Геннадий Семенович.
Нет, Геннадий Семенович должен быть первым открывать сессию, да? Не, мы оттуда не будем. Вот этот доклад можно перетащить.
Угу.
Вот.
Это ваше?
Да, я могу его доложить очень быстро.
Ну, понятно. Он вместо этого?
Да, если у тебя появится время. Сейчас мы его найдем, этого китайца.
Нет, а после китайца-то вот это кто имел в виду? Непонятно?
Ты меня спрашиваешь. Непонятно. У тебя, по-моему, первоначально распечатанное. Да, по моему докладу, конечно. Поэтому, конечно, можно, да.
Я по-русски тогда, да?
Да.
Нет, серединная строка. Значит, а если... Вот это, да. Вот если взять промежуточный случай, то между вот этими первым и вторым...
Вот этим?
Не. Вот вторая строка. Промежуточный случай углового момента. То что будет? Два сопоставимых пика? Что будет в этом? Не, налево двигайтесь, между вот этими двумя. Ну
где налево? Вот это, что ли?
Да, между ними.
Между ними?
Да, что будет?
Хороший вопрос. Будет плавное по непрерывности. I would like, the question is what happened with the situation when the parameter here?
Yes.
Maybe там как-то непрерывность будет по гидродинамике. Да, from the continuous theorem, maybe something mean.
Вопрос был, могут ли быть сопоставимы прекурсоры и GRB?
Могут быть. I would like to, if I have the time, I would like to explain what does it mean precursor and gamma ray burst in this model. The precursor, if you have collapse with very high angular momentum, much more than need for collapse to black hole, for example, very, very big. The collapse stopped at the radius where centrifugal forces stopped the gravitational forces. Okay? This understand. If you have избыток, как будет?
Excess.
excess. If you have excess angular moment, the collapse stopped at the some radius and formatted some object we call this spinar. After that, intensity of precursor depends on the angular moment. Then more angular moment, then less precursor, because with higher angular moment, the energy very small. Gravitational radius of spinar is big, and created energy is small. You see here, very, very small. Here, no precursor at all. It's hollow. Very, very small energy. But in situation with small angular momentum, all good. The collapse stopped near the Schwarzschild radius, no, Kerr radius. And energy is higher, like to gamma ray burst. So in this situation, you receive 2 is equal to more or less equal double GRB. A lot of GRB with double structure, a lot of. This you see, but this needs big magnetic field, because if the magnetic field is 0, this only viscosity is small. That is question. This is our picture. You see Plato, if the magnetic field is big, the first precursor represented as a gamma ray burst. Very, very magnetic field small, but stopped radius very equal to gravitational wave radius. The energy is big, evaporated. All collapse with higher angular moment have the 2 stages. First stage, when the nuclear of stars stopped at some radius where centrifugal is equal to the gravitational forces. After that, dissipation of the angular moment determines the time of next stage. Next stage, shortly, if that is dissipation of angular moment. This not maybe magnetic field, this may be viscosity, who knows. But if the dissipation is how, you have the short gamma ray burst, 2 equal bursts. If the dissipation is small, you have the Plato. This scheme was generated from the... Женя, у тебя нету этой расчета, нет, картинки? Ты не нашел? Ну, ППТ-шку кинь ему. Ты сможешь показать ППТ-шку? Вот первоначально эта картина рождалась для Плато, когда Плато открыли, и было несколько моделей. Вот, кстати, Zhang, которого здесь цитировали, и одна фамилия у них этих Занов, как у нас Ивановых примерно. Вот. Этот Zhang, он первым заметил, что если у вас рождается магнитар, как сейчас говорят, тогда говорили просто нейтронная звезда с большим магнитным полем, то у вас на первой стадии светимость почти не меняется. Ну, когда, это ясно, это там простая формула замедления и так далее. И он этим объяснял Плато. Но для спинара то же самое. Вот сейчас вы увидите, что у спинара та же модель, только в конце может быть коллапс в черную дыру. Послал тебе, нет?
Так, да что китайцы наш?
Давай я тогда это самое перейду к докладу из той части, вот там, где это самое.
Ну, давайте,
сейчас,
давайте я объявлю тогда.
Нет, подожди, не спеши. Мы еще, ну, поговорим насчет этого. Подожди. Ну, у нас 2 доклада еще. Находка такая.
Да, я про китайцев беспокоюсь.
А китайцы, как найдется, мы сразу остановимся и вызовем его к доске. А он свой файл присылал?
Нет. Пытался успеть в этот брейк, но не успел.
Кто пытался? Ну, он был жив там, что ли? Ну, ладно, сейчас, может быть, оклемается. Но у нас есть это самое... Данила, найди сейчас PL-диаграмму нашу, пожалуйста. Это будет как раз доклад вот из этой сессии. Вот этот доклад.
Тогда
да, вот этот доклад. Я сейчас быстренько расскажу, да и все. За 10.
Там есть у тебя, да? И диаграмма есть, все. Ну, давай. Ты пока китайца ищи. Ну, мог бы. Видите, Данила у нас многостадойщик, и приходится и одно, и другое, и третье. О, вот и все, давай.
Because our colleague YiQing GUO did not connect, the next report will be by Vladimir Lipunov also.
One of the co-authors of the... Ты объявил этих, нет? Название доклада тоже нет?
Нет, конечно. Названия нет.
Да у него распечатка такая.
У меня нет.
Ну, ты надо было подойти и спросить.
Так я подошел, спросил.
Кто-нибудь распечатайте программу, у вас же у всех есть, ребята, кто... Давайте уже в перерыве лишь. Нет, не надо мне так. Вот, ты же это самое... Magnetars part of Neutron star. Это вот такой доклад. That is a short talk, which, unfortunately, Danila here, but Danila have another talk, and he now found next talker from the China. Valeria Greenspan, very long distance now from us, without internet, and so I am so closer, I am sorry. This talk was planned to present after the very interesting session with opened by the Gennady Semyonovich theoretical work. But in any case, this not depend directly with the previous and post talks. So, and several months ago, we published the paper, this co-author, in the astronomy, the New Astronomy Review, about the general diagram of neutron stars. That is very old idea, that the only... Наташ, дай ему с названиями, он мучается, ни названия нет, ничего. И китаец потерялся, он был в перерыве, Наташа. I'm sorry. А? Ну, а поговорить с ним нельзя? Ну, давай. Хорошо бы, если бы он начал сейчас выступать, потому что я бы с удовольствием как раз после Геннадия Семеновича там, где мы были, потому что это как бы он открывает сессию. Нет, ты не ожил, ты скажи, когда он будет готов. А жил. Понятно, что он не мел. Ну, вот этот подход, он давно родился в команде Зельдовича. Я думаю, что первые работы были на эту тему где-то 69-го, 70-го. Тут есть люди, присутствовавшие при этом начале. Вот Геннадий Семенович, в частности. Это речь идет о том, как себя проявляют вращающиеся замагниченные компактные релятивистские звезды, ну, нейтронные звезды фактически. На самом деле эта картина развивалась несколько лет и десятилетий, даже где-то в конце 70-х годов. А я хочу напомнить, что все работы по аккрецирующим нейтронным звездам были написаны в группе Зельдовича. Ну, одна с Фридманом, да, Фридман там появился как бы не из группы, но там, по-моему, соавтор был Геннадий Семенович, да? Фридман. Геннадий Семенович. Ну ладно, он готовится. Вот. И выработалась такая точка зрения, что очень интересно посмотреть, very interesting to see on the neutron stars as the object with a very idealized, but object which have the gravitational parameter mass and angular momentum of the spin and some magnetic dipole field. And three parameters can be explained a lot of manifestation on astrophysical manifestation of neutron star. Initially, very old idea. I don't know how many. And in this case, the stage of neutron stars, a stage interaction between neutron stars and background plasma, may be considered as a relation between two fundamental radius. Radius, stop radius, there's some mistake, stop radius, radius corrotation, light cylinder radius and gravitational Monty-Hoyle radius of the accretion radius of the neutron stars. Two last parameter give us reflect the electromagnetic and gravitational interaction between the neutron stars and environment plasma. You see, two parameters is very suitable because I can show all parameter on the one diagram. Well, you see this different table of different stage, ejector, propeller, accretion, so. This published very old. That is the sum finish of our attempt to understand very first approximation of understanding of the neutron star interaction with surroundings. And you see here diagram after 30 years, maybe 40, I don't remember how, we, with our more young colleagues, we try to understand where is on this diagram is a lot of different compact objects, accreting, non-accreting, ejecting, and so. And this diagram here, that is, а как я вот им покажу? Ты будешь показывать? Нет, это не надо ко мне подходить. Как они увидят? А есть мышка? А, она вот здесь. Извиняюсь. Вот это самое. Вот on this diagram you see different, that is axis period. Да елки-палки. Нет, ну зачем это она перешла? Вот, что, мышка работает, что ли? Нет, давай микрофон не будем выключать. Он сломается. Да черт с ним. Very complicated. Окей. И что мне теперь делать? Этой мышкой, что ли? Ну, хорошо. Mechanical mouse. Okay. You see, that is a period, spin period of the compact object. This may be neutron stars, maybe white dwarf. That is a gravimagnetic parameter. Y is proportional accretion rate divided to square of magnetic dipole moment of the object. In this diagram, you see these ejectors, this well-known radial pulsar here, that is millisecond pulsar, and that is the magnetars. That is the propeller stage. Its stage is very short in the evolution of neutron stars. That is the so-called polars, that is white dwarf polar system, magnetic field with very high magnetic strength on the surface, so-called the polars. Initially we M class, and here you see accreting neutron stars, and you see the different type of observed neutron stars and white dwarf on same diagram simultaneously, because all physics existence of these stars here explained only interaction between gravimagnetic rotator with the surrounding plasma due to electromagnetic and gravitational field, two forces. That very you see here more firstly this diagram with modern object which detected last 30 years in the high energy relativistic astrophysics, X-ray binary, so I shown on the St. Petersburg Franco Giovanelli symposium with cataclysmic and exotic process in the binary system, which he referred in his remarkable talk. But I come back after to Moscow after the symposium. We look to this diagram and found, you see, this line of the usual, this dash line of the usual parser, the parallel to this line that is discovered by Schwarzman in 1970 in astronomical journal, published a paper with so-called the two generation of pulsar. At that time, no accreting pulsar discovered. That's very nice job. And we found it on this paper and give the formula on this diagram. And this line depends only these two parameters, no another parameter. You see here no pulsar because here the ejected relativistic wind died, collapsed, no wind. Here the propeller effect, no bright sources, some X-ray pulsar here. And you see here the magnetar, because in next session we will talk about magnetars and fast radio bars and very popular phenomena is this now is a lot of paper in press and popular paper and so we try to find magnetar on this diagram. You see here that is a magnetar from point of view of the gravimagnetic rotator paradigm. The magnetar not differ from another radio pulsar, only in its position, because magnetic field is very big, so the Y parameter is very small, and we see long periodic pulsar. We detected a long periodic pulsar as a magnetar. So the spin down time is very small. And so magnetar is very naturally come to this life diagram of life of neutron stars. And I come back. Three population, high magnetic neutron star, low, middle magnetic, and the low magnetic, different type. You see this line parallel to the Schwarzman line, this line parallel, this line propeller accretor, so-called spin-up line. This only one diagram in nature where you simultaneously can you see naturally neutron stars different types, X-ray pulsar and radio pulsar. Why this parallel? You see here very good angle. You see on the next slide. This may be explained only in the evolution by the evolution properties of the neutron stars. The first properties well known in astrophysics, well known. You see the people now understand that the millisecond pulsar that is a result of evolution of the low X-ray binary system, low magnetic, low massive X-ray binary system. Because this system, lifetime of this system, about several billion years, magnetic field disappear. So spin-up line, spin-up neutron stars come to the millisecond period, but secondary donor give accretion to these neutron stars, disappear after the nuclear of stars, как-то отщепляется, как бы сказать, split from the Roche law. And after the split, in some case, we give the neutron stars, millisecond neutron stars, with planet. but or a very, very small nuclear of the old star. But millisecond pulsar gives a very, very strong relativistic wind, which evaporated binary component, second binary component. If you see millisecond pulsar without any component, but the pulsar, of course, come from the accretion process. That is very interesting. Why this inclination parallel to this line? This line, we agree with the idea of Schwarzman. This line gives us a moment when the relativistic wind pressure is equal gravitational dynamical pressure of surrounding plasma at the Bondi radius. Bondi radius. If the plasma pressure bigger, all this caverna, Schwarzman called this caverna with relativistic wind, collapsed. And in this moment, radio pulsar died. This inclination was known maybe 30 years. And you fully parallel. Okay, this magnetars, higher magnetic field, all people say that the magnetars have origin from the very massive star, young massive star, because last 10 years, 20 maybe years, magnetars was found in the very young globular, not globular, I'm sorry, very young cluster of stars with very massive stars, blue, 20, 40, 60 solar mass. And so I have the long discussion with, with my opponent in the journal and the redactor. He said me, all people know that the magnetar comes from low massive, I'm sorry, from the higher massive binary system, from higher massive star. What do you think? But we propose a scenario when the magnetar can become from the white dwarf. In white dwarf population, in here you see polars, 100, from 100, several 100 mega Gauss white dwarf. If in binary system with gross mass, if the mass come to Chandrasekhar limit, this these polars directly come to the magnetars region, because this is the records of the magnetic field in white dwarf population, as магнитар is как этот рекордсмен, leader in magnetic is between neutron stars. One leader produced another leader. But our paper 1 year not published because people say, no, magnetars come from the massive star. In your scenario, it does not work. But during this discussion, astronomers discovered magnetar in globular cluster, when no massive star at all. After that, all okay, we published the scenario. You see, this I not say we not say that the only one way of formation, as usually the nature is more complicated than we thinking about it, and we have several branch of formation magnetars. Two here direct formation from the massive star, blue, formation by collapse from induced collapse from white dwarf, and maybe merging of the two neutrons, two white dwarf, onion magnum white dwarf, very heavy white dwarf, can formate the neutron stars with very high field, and can formate supernova time 1A simultaneously after. Now exists at least 4 different ways of formation magnetars. The nature is very, very как это сказать, дерево такое разветвленное. А? Да, но не так, как у меня на голове, а вот когда много-много разных вариантов. Наоборот.
Хорошо. Вот мы попытались все-таки вот этот вот we try to simulate this branch of formation magnetar by induced collapse of the very heavy magnetic field. And you see here that is the Danila, that is the initial, да? That is the initial distribution. So that is the observational histograms. We approximated such empirical distribution for the simulation. Monte Carlo simulation, small scenario machine, piccolo scenario machine. And after that, that is initial white dwarf with such magnetic field, this observational data, that is our computers simulated, but we try to see what neutron stars can be. You see here, the period of the formated neutron stars, this one, is very good. Exactly, is equal 10 seconds. For me, I remember this time in 1980, maybe 4, 3, the ECO even come to the Alexander Tutukov, ECO even well known famous nuclear reaction and so evolution, usual stuff. And I tried to explain him how to formate neutron stars from white dwarf. 1 hour and 48 auditorium. I don't know if he understands or no, but we include this scenario. Here, yellow, this observation. That is our result. Of course, very, very, very smoothly, as the usual. Calculation is much more ideal than our observation. But in any case, all magnetars stay here from the 5 to 20 seconds. It's good. But after the appearing this paper, was discovered magnetar with period 40 seconds, да? Дима, не спи, скажи мне, пожалуйста. Super long magnetar was detected several, maybe
12 секунд, по-моему.
Не, больше, 40 секунд. 10 to the 14 Gauss. In principle, the tail is very long in this calculation, but situation with magnetic field is no good because we see that is our simulated magnetar, that is observation. You see some discrepancy. But I explained this, you understand, we use a very simple model. If the white dwarf if the mass white dwarf come to Chandrasekhar and collapse it, we proposed that the magnetic flux is constant. As its minimal assumption. But really, some generation process, no people excluded. Of course, if you see on the measured neutron star, the typical age of these neutron stars from our scenario machine calculation, about 70 million years. On this median age, several dozen million stars. This is not young star, this is not magnetar. But during the merging and the alpha generation of the dynamical, как будет по-английски, динамо? Ну, не важно. due to the dynamo amplification of magnetic field, you can receive a magnetar. We not include in our calculation, but period is good. And I remember, I finished it. When the YiQing say, why do you think this very strange scenario? Why? Because all first discovered magnetar have the period 7 seconds. You remember this, no? If you remember the 5 марта 1979 года. Какой период был? The period of the first short gamma repeater, да, или как он называется, 1979 was 7 seconds. After that, new type, strange X-ray, как они называются, странные пульсары рентгеновские по-английски.
Аномальные рентгеновские
пульсары. Animal pulsar. 7, some...
6 до 12 секунд.
Yes, it's very interesting. Why? No, first time only 7, 8 is a fundamental period. But we see that the period is very simply explained in this scenario. But not, I cannot to explain this period from the direct collapse of massive star or imagine this another physics. Okay, in any case, thank you very much. I'm sorry.
Thank you
for my English.
Please, questions?
Hello?
Нажми там, пожалуйста. Дай покажу.
Pulsars. They are lying along previous, this one. Yellow dots. So yellow dots. They are lying along this solid line. So probably there is some analytical expression for this.
Of course. You must understand this universal simple approach needs some simplicity for the simplicity co-authors like to me. I like the analytical expression. Of course, the good question. Why this line is very yes, because this low magnetic field neutron stars. No people see any magnetic fields at all, but see only period. How I can found magnetic field? There is some method. I propose it that this billion years evolution, this very long life of neutrons, very old neutron stars, and these neutron stars have the equilibrium, quasi-equilibrium period was very simply found from the spin up and spin down moment of the accreting moment. So you see, of course, that is the analytical expression of our understanding. I note, for example, that you see here M with dot. We do not know excellent M with dot for this pulsar. I put the mean density of interstellar medium and the mean velocity of neutron stars. You understand me? Yeah, I don't know, some theoretical assumption. This diagram, maybe in long future, determined all parameters, but now we must understanding we must have general understanding how live these neutron stars. What type of neutron stars you can see on the sky, because this diagram supply in the 1980s years in scenario machine where we predicted a lot of manifestation of neutron stars in binary system which no people observe it. For example, we predicted radio pulsar with a blue star, not observed at that time. We predicted, for example, a white dwarf ejector. You see, there's a white dwarf radio pulse. That is white dwarf. There's not neutron stars. So you understand that, but for the more dipole approach is very, very complicated. You know, there's a magneto-hydrodynamical problem in gravitational wave, in gravitational field. No any analytical solution in this problem at all. No any accurate, как сказать, mathematical, no, нет, computer calculation, because if you put something to computer, you receive same result. This depends on what you think about it. But no people, it's very complicated. You understand, this problem very like to problem of the tokamak. Tokamak is the people, physicists, try to produce electro energy from the nuclear fusion, yes, but no successful. Why? Because this magnetic field and plasma, the same problem. In tokamak, plasma inside magnetic field, here plasma outside, but here you must say that the gravitational. In gravitational, no. So, for example, I remember Zeldovich, we now met here with in the frame of Zeldovich astrophysical seminar, and he said me on the, I was student, he said me, no analytical solution in the self-gravitational hydrodynamics. Самогравитирующих. Нет ни одного аналитического решения, если вы запишете самогравитирующие гидродинамические уравнения. Нету. Поэтому следующий шаг будет, даже не когда появится компьютер, а когда люди поймут, а что там вообще-то ждать оттуда в этом случае. То есть это грубое первое приближение. This is a short approximation. Of course, this border is very important, and maybe new, unpredictable events may be on the border. Border, this means I cannot use, я не могу использовать эти упрощения, которые я делаю вот здесь и вот здесь. На границах происходят какие-то новые явления, но до границы еще, смотрите, сколько. Magnetars, intermediate polars, low mass X-ray binaries, V star, Wine-Find X-ray, millisecond pulsar, white dwarf pulsar, intermediate polars, propeller effect, extragalactic ultra-luminous X-ray sources. You can see, you can find conference on each this object in the International Astronomical Union. So that is like some simplicity to understanding. That help for your intuition, not more, but very successful, as we see from the scenario machine result. Okay, I'm sorry.
One question, comment.
Я хакала Пугачева на арене, надо что-то делать.
I like this diagram. I see here some analog of Hershman crystal diagram well known. So you succeeded to put in one diagram all on magnetic rotators. So neutron star, white dwarfs, I would add AP stars, magnetic.
Maybe, but we don't see period.
To study this and to study.
Yeah.
And now, next natural question arises, how to use the diagram to put some evolutionary tracks. Now, could you immediately make some point, and how it could be, how it could evolve due to accretion, aging, and so on?
Yeah.
So evolution острый недостает эволюции.
Okay, I can answer.
It's a question.
Yes, my answer next. Okay, we included a simple equation of evolution. Equation of evolution is a slow changing of the angular moment of the compact star, depending on the forces, accreting moment forces. Very simple equation. In binary system, we can found the accretion rate theoretically, okay? Angular moment, disk accretion is very simply. Wind accretion is very complicated, but more or less some approximation, we can use it. And of course, in the scenario machine, every scenario machine calculation, we use it billion tracks on this diagram. I agree with you. You can find very old our paper and found some different prediction. And I forgotten to answer you. Why for Александр Васильевич, я ответил на ваш вопрос, да?
I would like to see некие схематические треки.
In the Franco Giovanelli talks, he shows with tracks from my yearly paper. There is a tracks here. Very good question. But this, I would like, I don't know, if I put here all tracks, the diagram, is very, not very beautiful color was. Brown. Я согласен, но не знаю, есть у меня это много раз публиковалось, Александр Васильевич. Просто я скромный человек и не показываю. Ладно, еще есть вопрос? Давай.
Так, появился китайский товарищ.
Ура! Надо показать.
YiQing GUO, are you here?
Okay.
Okay, you are ready?
Ready.
Yes, please, you can begin, but just to
I have put my input in the web, but how can I show it?
Ну что, он появился там? О, конечно. А кто это? Ух ты. Так это LHAASO знаменитый.
Да.
Yes, sir. Okay. Can you hear me?
Yes, we hear you. Please begin.
Yes. Let me begin my talk. My topic is search for very high energy emission from gamma ray burst with LHAASO experiment. Okay.
А кто переворачивает его? Он сам?
Да, по идее, он сам должен.
По-моему, он не может.
Okay.
О.
This is the main content. Firstly, I will briefly give a short introduction. Then I will introduce the LHAASO experiment. And this knowledge, I will give the LHAASO sensitivity of GRB. So, the LHAASO disk sample and analysis preliminary result. The last one is a short summary. Oh, very slowly.
All okay. Very good.
This is the figure for the GRB fiber model. Many other colleagues have given more information about this figure. So here, I only want to see about the high energy gamma rays in the internal circle of the perimeter phase and the actual phase of the optical loop. So the high energy gamma ray in the internal circle is very, very important for the nature of jet information and relative outflow, shock acceleration, and other physics. So in this work, we pay more attention on the high energy gamma ray at the internal circle. This is the progress for the observation. Here, from the discovery and study and other high energy before 2019, before 2017, this is the sky for the space-bound experiment. After 2017, it is the ground-based experiment, like LEGO, discovery the gravity wave and GRB. More important is the magic and health. Open the sub-TV window in the GRB physics, but there is zero observation for the sub-TV at a perimeter phase. Sorry, the net is very, very slowly. I cannot show that in my computer. There are three kinds of experiments: the space-bound here and the ground-based experiment. In the left channel, it is the ACT technology experiment. Here is Vapor, Hash Magic, and Veritas. Here, this kind of experiments has a low threshold and high sensitivity at high energy, but the limit is very, very small, the field of view, and only 10% duty cycle. In the right panel, it is the ES array, such as Mirago, Eta Gamma, Argo, and Hawk, OK, LHAASO. This kind of experiment has large, wide field of view, but has at low energy, the sensitivity is very limited. At low energy. So, if we want to see the perimeter in phase, maybe we need the ES array. This is the space-bound experiment for high energy observation. The left one figure is 1 GRB. This is the J1 name, 1 GRB for the observation. In the low energy, this is a band-like function energy spectrum, but at high energy, there may be one actual component for high energy, but simulator has a limited area, only limited number photons. The spectrum for the high energy is very, very limited. So, for the space-bound experiment, the high energy measurement need improvement. So, we want to see the ground-based experiment. This is the sky for the GRB observation. It is for magic health. There have 6 GRBs at sub-TV measurement. But you can, from the list you can see, the time observed is after tens of seconds. In the initial time of the prompted information, there is no observed. It is repeated only afterglow phase. If we can observe at the first tens of seconds, we may need low energy threshold, wide field view, and full duty circle, high sensitivity experiments, which experiment can. Okay, let's see LHAASO. This is the LHAASO bird view. In the center, there's the core building. This is the LHAASO WCDE. Here, we search for GRB by using the LHAASO WCDE. This is the experiment of LHAASO. In the central, it is LHAASO WCDE. In the circle, it is CAM2E. The LHAASO has a high altitude and larger detector area. For here, the area is for WCDE and wider field of view, full duty circle. In the LHAASO WCDE, there are 3 poles, pole 1 and pole 2, 3. Pole 1 is the PMT is only 8 inches, but for WC2 and 3, the PMT is about 20 inches. It's very, very large. The larger PMT can lower the energy threshold about 100 GeV. So, let's see the LHAASO sensitivity. This is the LHAASO and other experiment sensitivity for Crab. Here, if we use only 8 inch PMT at low energy, about several hundred GeV, is very, very worse. But we use 20 inch PMT, the sensitivity at 100 GeV is improved. Here, we can see at TV energy range, the Crab sensitivity is 2%. At 100 GeV, the sensitivity for Crab is about 10%. So maybe LHAASO experiment is simple to search for very high energy gamma ray from GRB. The sensitivity for GRB is necessary for LHAASO experiment. Here, we first give the GRB sensitivity for LHAASO. In order to give the sensitivity, we developed one software package named GuoEyes. Why named GuoEyes? Because GRB is the good eyes to see the deep universe or cosmos. Here, many colleagues has given presentation. There are many missions in space to observe the GRB, such as Fermi GBM and later, and BEAST, Egret, Swift. We want to see every mission maybe see the GRB 1 point of view, but the whole GRB information maybe we need to combine all the mission. So we want to know, can we give a ideal sample? This sample, GRB sample, can also satisfy every mission. If so, this sample is very, very good, and we can do many physics about GRB. This is our software named God Eyes. The right one is the package framework we have finished. In this work, we only certify the Fermi GBM and Fermi lit observation. In the future, we will give some other mission like BEAST, IGRIT, and SWIFT, and many other experiments. By using this code, we have published 3 papers in APJ and another 2 papers in preparation, and some other work on the way. Okay. How to get the D sample? In the GRB, maybe we have some important parameter, such as the spectral, the space distribution, and the temperature. About the spectral, maybe we use band function for the low energy and one parallel spectral for the actual component. Here, 3 power index as alpha, beta, and beta actual. Alpha beta is for band function. The beta actual is for the actual component. Then we should know the space distribution of the redshift and fluence and e-peak and the T90. If we know those parameters, we can give a sample. This is the technology. Here, we can using a GRB generator to generate one sample of GRB. It from the cosmos propagation and EBL attenuation. After those, we can test the experiment test. If this group GRB is okay, we can do physical result. Is not okay, we are using the multi-net training, give a global fit, and again to give another group. By loop and many loop, we can train one group of GRB sample. Okay, this sample can be tested by the baseband experiment. This is for Fermi GBM and Fermi lit test. The first figure is for redshift. It is roughly consistent with the observation. This one is for the fluence. It's also very consistent with the observation. This is alpha, beta for the band function, and this is for the e-peak. This is for the T90. All those parameters is consistent with the observation. So we think this is a quasi good sample. Now we using this sample, we can give LHAASO pushback. Here is LHAASO sensitive. In the left panel, the figure is for 1 GRB cartoon. At low energy is a band function. At high energy, there is the component, actual component. Here, the actual component only use the ratio with the total energy and the power, only 2 parameters. By this spectrum, we can see LHAASO can observe how many GRB in 1 year. The right one is for the observation for LHAASO. The red line is for we cannot consider the actual component, only band function, about 0.4 GRB is observed in 1 year for LHAASO. The blue line is for the actual component. The ratio for the energy for the supercomputer is only 10% for the total energy, and the spectral is -2. And this GRB spectral, the LHAASO can observe the 1 GRB in 1 year, and we can try other parameters. It's more. It to see if the actual component is more energy, LHAASO can observe the more GRB. In this model calculation, we don't consider the intrinsic energy break in the GRB. So, it will see LHAASO has some potential to observe the GRB. Now, let's see the GRB data sample for LHAASO. In order to search for GRB for low energy, we have a special data mode. Here, there are 2 data modes for GRB physics. One mode is the GCN alert. We get alert, maybe from FEMI and Swift. If this alert give, we will check this GRB is in LHAASO view. If in LHAASO field view, we will keep all the information, all the hit in the disk. Here, for this GRB, before half an hour and after 2 hours, we keep all the emission, all the data emission. This is for the trigger list data. Another mode is for the triggered data. This is normal data mode, like other source. Maybe that all the data can keep it. It's only for the show mode. By using the trigger list data, we have taken from 2019 year, only WC1 take the data. 2019 to 11, we have 2 pool, WCD1 and WC2. In last year, we have the full array. In this talk, we have using the full array, the data. This is the GRB number for LHAASO observation. Here is for the W1, W1, 2, and the blue one is for the full array. We analyze those data. They are about more than 100 GRB in our view. Now we will check which GRB can be used. Here, the first one is the zenith angle. We require the zenith angle less than 50 degrees. Here, after this selection, only about 100 GRB is kept. And also, we need the good data taking condition. About 1 year, there are for trigger list data only 89 samples. And for the tree data is about 100 samples. Here, in this analysis, we only analyze those GRB. This is for the data analysis for the trigger list data. In the low energy, the bottleneck problem is the noise. There are many noise from the cosmic ray. How to reject the noise is more important for LHAASO low energy reconstruction. Here, we using the GRB information. If we know the gamma ray direction, the solar front is very thin. So we can only choose selection the thin disk for the front, short front. So we can reject the noise. This is the art for the data construction for JRB data. This is a cartoon. Now let's see one event. Here's one event for Monte Carlo gamma ray event. This is about 300 GeV. Here, the red one in the left panel, the red one is noise. The blue one is for the signal. The signal only in the thin disk. This is the short front. So, if we know the JRB direction, we can choose this direction. So, we can choose the very thin front. The noise, red noise can be rejected. In the right one, it is event from the projection from y-axis. See here, the noise can be rejected very effectively. After the noise rejection, now we're using the space information. As you know, the gamma ray in the atmosphere is like an NKG function. It is a literal distribution. After the short front selection, now we select the space. Only near the core, we select the heat information about 50 meters. So by using those select heat, we can get the record the data. After data reconstruction, now we will give an analysis. Here, we use on-off window to estimate the background, also sideband function. Here, the signal signature can be calculated by lemma formula. In this analysis, we analyze the parameter phase and early afterglow. Here, we first select one JRB as an example. We select this JRB as an example for the data analysis. This JRB is alerted by Swift and also by FIM-GBM. It is in LHAASO full view. This is the thinnest angle. Also, FIM-GBM gives the fluence. The fluence is very large. So we select this JRB to analysis, give analysis. In the left panel, the up is for the event data rate. In this panel, data is for on window and sub-select off window. It is signal, only signal. Here is a large curve. We cannot see the significance. The blue panel is for the significance for every second. Here, we cannot see the effects. The right is for the distribution of the significance. This JRB, we cannot see any effects. Use this method, we can analyze all the JRB. Here is we analyze all the JRB. For 89, every JRB can give a significance. We put here, it is a Gauss distribution. So, from this figure, we can see, until now, we cannot see the effect for JRB in the parameter phase. Okay, this is a trick data analysis. Now we can continue the data analysis for trick data. Before analyzing the JRB sample, we first analyze the credible source. By using the credible source, we can give the standard selection and take the signal. This is only 73 days credible. Here is the significant case, and about 80 sigma. We also, by credible analysis, can give the angle resolution for every energy. This energy about 100 GeV. This is about 500 GeV. This is about TeV. So at every energy range, we can give the selection criteria, such as the angle resolution and the gamma separation. By using this standard analysis, now we also analyze the GRB example. For this GRB, it is the same with the trigger list data. Here, by analysis, we can see in the trigger data, we also observed no excess signal. Here is the significant distribution at 3 times. So for this GRB, we also cannot get the excess. By using this method, we analyze all the GRB. This is the distribution for all the GRB for the true data. For every panel, it is for different time, different energy. So here, there are no GRB observed above 5 sigma. So until now, we cannot see the GRB excess in LHAASO experiments. So this is a summary. Until now, we analyzed all the GRB in the full array, but no excess is observed. I think there are two reasons. One is we need more data. The other is in the low energy, we have some space to improve the sensitivity. In the following years, we will improve our sensitivity at a low energy. And also, we need more search for high significant GRB. That's all. Thanks.
Thank you. Please, any questions? Please, Alexander Tutukov.
Thank you for talk. I see a big experiment. Could you answer two questions? First one, what is expected lifetime of this experiment? And second, what is the approximate price of this experiment? That's all. Two questions. Lifetime and price.
Can you hear questions?
Could you understand?
Okay.
Do you hear questions? There were two questions. First, what is the approximate time of experiment?
Lifetime.
Lifetime of experiment. What is approximately lifetime of experiment?
Oh,
And price. What's price?
we only analyzed 1 year, about 1 year.
But future.
For future, how long will the experiment? Several years, maybe 10 years or more long?
Maybe,
In future.
but maybe this experiment maybe very long time.
Long time. And what is the price
Yeah.
of experiment? Is it how much money need to prolong this experiment?
I have no knowledge about the money for the experiment.
Говорит, что это что-то там зависит, но не можно ответить. Не можно ответить. And one more question. That fact that you did not yet detect any very high energy GLB, what is the reason? It is limited statistics, or there are some physical reasons? Maybe there are no high energy emission from GLB sources. What is your opinion?
Yeah, there are two reasons. One reason is at low energy, we need to improve our sensitivity. The other reason is maybe we need a more strong, more powerful GRB.
Oh, you will wait more powerful GLB. I see. Yes. Okay. As I understand, you will wait more powerful GLB.
Yeah. More powerful. Yeah.
Okay. One more question. Zahar, please.
Okay, do you hear me? Okay. It's by the way, I would like to ask. First, he said that expected rate 1 GRB per year, but they worked only for 1 year. So they gave. But I have a question about previous slide. About when you showed map of your facilities, there are some empty zone in your detector. When you show, could you explain reason to have some empty zone without?
I think your question is very interesting. Here is but 1 year for 1 GRB observed. Here we have a theme. A theme is have a actual component. Also, we cannot apply the intrinsic energy Greek. So, if we give the observation for the whole time, maybe we can control the emission. Yeah, maybe the intrinsic energy is not considered.
Any more questions? Let's thanks again. And I would say that report master AAC highlights from master team will be moved on the evening session.
Okay.
That's the